Right. Things only continue to get worse. As I said, they were in a situation of complete contradiction. Nobody understood anything about what to do, and it was what's called the old quantum theory, which basically looks like, to me, books of black man. You open up these books, and they have like, then you do this, and you do that, then you make this guess, and you make that guess. So a Frenchman came along in 1923. His name is Louis de Broglie. Louis, in his PhD thesis, asked the following question. He said, from reasoning from the photoelectric effect that we talked about before, he said we should ask the question, if photons have a twofold nature, which we just said they did, they were waves and particles at the same time, why not apply the same principle to electrons? Why not say that electrons might also have a twofold nature? That we think they're particles, but maybe they're also waves, he said. So he made an assumption that, reasoning from the idea that in a photon, energy is equal to the h times the frequency, he said in an electron, momentum is h over the wavelength. This is the same basic equation. And 1 over the wavelength is like the frequency, so you should be aware that these equations are very, very similar to one another. And he wrote that down and said we should test this conjecture and see if it makes any sense, and sent it in as a PhD thesis, which was immediately rejected. He said, no, there's no way you can graduate with that. That's just stupid. That was rejected. He got upset about it. He wrote a letter to Einstein in which he said, I don't really think this is that bad. What do you think? Einstein wrote back to the authorities at the university and said, this is the most brilliant PhD thesis you've ever seen in your life. If you don't graduate this, you're a complete idiot. And they're out. So that's the way the cookie crumbles, but we were fortunate that it actually worked in this case. Okay, so Louis said particles were waves, which means that we can have a two-slit experiment for particles. Now, for classical particles, the two-slit experiment looks different than it does for waves. I already talked to you a little bit. These are pictures from Feynman. I told you a little bit about what happens with waves. You go in here, you get the two sets of waves coming out, and they kind of add up to be this thing with light and dark peaks at the end, up and down, up and down. If you do that with regular particles, like a gun that shoots bullets or something, and stuff going through one slit will make a distribution that looks like that. It kind of bounces around a little at the slit so it doesn't all come out straight to the center, but you get a distribution that comes out and looks like that. And the other slit, you get a distribution that looks like that. And when you finish, you add up the two distributions and you get something that looks like that. So that looks completely different from this. So particles and waves have totally different behavior under a two-slit experiment, for which we really need that information. So this is the particles, and there they go. You're going in, thump, thump, thump. Oh, that one went straight through. Oh boy, hot dog. This one bounced. Yeah. This somebody mentioned that this is like a very old computer game. Okay, but now we have waves, and they're going to behave differently. Yeah, okay. They're coming all at once for one thing, and they make this pattern of dots and dashes. Particles make individual clicks as they hit the thing. The way they used to do these experiments is they had screens with phosphors on them, and they put a little microscope on there and they count the little dots. No computers in those days. It was tough. It was tough. Between drinking tea and sherry, you had to sit there and count particles. It seems like a very strange idea that electrons would have a wave nature. So, but it was verified by Davison and Germer, who were working for the phone company, which used to be a massive research enterprise in the United States and was dismantled in the 80s. They were working for the phone company, and they put together an experiment. I got this out of a German book. So an Elektronenkanone shoots down to the nickel crystal, which then goes to the detector. And they shot these. They shot electrons at a crystal and bounced them out. And you could, if you have a crystal that bounces something, or for light also, this serves almost the same idea as the two-slit experiment, except that it's reflecting. And they got this pattern as a function of energy. It came out, went out, came back down in. Typical diffraction pattern, but with electrons. Proved positive, certain 100%, that the electron had a wave nature. In fact, if you wrap it in a circle, take a proton and wrap these waves around themselves in a circle, if you do just the right number of times, they'll add up on top of each other as they go around. If you do it the wrong number of times, they'll miss, and eventually you'll get nothing. So when wrapped in a circle, see this one misses here? The idea is that this will eventually go around and average out to 0. When wrapped in a circle, the de Broglie waves naturally close on themselves. So if you put those simple equations we talked about, which I don't expect you to remember, but if you put those equations into Bohr's radii theory, formula, which we took from his model, you get this. 2 pi times the radius, that's the distance around, is equal to n times the wavelength. So it just means that if you have n wavelengths, 1, 2, 3, 4, 5, 6 wavelengths in this case, going around, and they go around just right to match up, then you get Bohr's thing that he made up. So that says that the waves actually have something to do with reality. These waves have enabled us to understand what's the physical origin of this criterion that Bohr made up to fit the data, basically, of all the spectroscopy. And somebody made a nice picture of an atom that consists of these different waves going around like that, straightened out, and you wrap them around here like this. Now this is in 2 dimensions instead of the 3 dimensions, but it really doesn't make that much difference, it turns out, for this particular application. The Bohr orbits are the closed waves that we see. For electrons, and we do the 2. So just to make a summary, for electrons, when we do the 2-slit experiment, the wave nature appears. However, each electron gets there as a lump. It doesn't travel like a lump, but it gets there as a lump. We say we don't know what path it took. Nature, the wave nature means that this thing has sampled both paths. So you get an electron here, you say, did it come this way through this hole, or did it come through this hole? Well, we say it goes through both holes. The electron is a wave at this point. It's going through both holes at the same time. You have to do that in order to reproduce the pattern of bright and dark that you see at the end. This should really be messing with your head at this point. I mean, you guys should be pretty uncomfortable.
How does the electron go through both holes at the same time?
Well, I'll show you. The prestigious internet will show you the answer. So this is the number of electrons versus position on the screen. There they are building up. They come in as lumps. I can make this go faster.
This is really small.
It's even more small.
This is like touching.
And they're building up. Each one gets there as an individual thing. And we say, okay, we know, we can measure, we'll just histogram. This is called a histogram of where they land. But each one lands at this given point. We put a tick mark in there. And we start to get something strange. We start to get a pattern of light and dark bands. The only way that I know of that you get a pattern of light and dark bands is by interference of the wave with itself. The only way it has to go through both, which requires the presence of something going through both holes at the same time. If you actually cover up one of the holes, or worse, if you put something at one of the holes that tells you which one it went through, something that flashes, a light bulb that flashes when the electron goes through the hole. So you put on the top hole a light that flashes.
So it acts weird when no one's looking, but when you're watching.
If you watch it, if you put that light on the hole and make this picture, this pattern will disappear.
So it doesn't like to be watched.
So it depends on when and where you are watching. If you are making it observable, you've done an experiment at the other end of the hole, and you get a different result. So it behaves like a wave during the period when it's not being when you're not observing, and when you're observing, it typically behaves like a particle. Okay.